Felix. Thanks, Rahul. And I guess this is also thanks to my physics background that this paper came into being. So I hope you guys can hear me. This talk might be a little different from the other talks. I think I'm going to spend a lot of time introducing the basics because one problem I had with this paper is that not many people are familiar with all the concepts. So I'm pretty sure almost everyone knows what a convolution is. I think not so many of you have seen tensor networks. And some of you might have seen Einsum or even used Einsum in their code. So the goal for this talk will be to give you a proper introduction into what are tensor networks, what is their relation to Einsum, and then we'll spend the last 5 minutes to do some cool stuff related to convolutions, and I'll show you that this is not only a really cool tool that you should learn, because I actually use it a lot, but that this also is really cool for making algorithms faster and simplifying understanding. So why this paper? I'll start with my personal journey, my personal struggle with convolutions. I work on algorithms, which means that I have to write low-level code sometimes, specifically in the view of optimization. And one thing that I had to do back then, a couple of years ago, was to write what is now known as a V-mapped vector Jacobian product. Don't worry about anything. So in the code snippet on the left, you can see how one would implement this for a linear layer. You can see the function is mostly documentation, 3 lines of code, that's it. On the right, you can see, I mean, you cannot really see it, but you can see there's a lot of code. There's not so much blue, so not many comments. You can see how to do this for a convolution, and the takeaway here is that this is much more complicated, and maybe this shouldn't be. So by the end of the talk, we'll be able to reduce the snippet on the right into 3 lines of code. And I'm not the only person that kind of went through the struggle. There's a lot of those patterns showing up in other research branches. So people working on algorithms, people working on theoretical studies. It's very common that people start rolling out their ideas in the context of MLPs. And then a couple of years later, someone applies the same idea to CNNs. Sometimes even 30 years later. So the whole goal of this paper was really to come up with a simplifying perspective that allows convolutions to be treated, let's say, almost as easily as linear layers. And I want to quickly just give you a rough notion of why convolution might be more complicated than a fully connected layer. I mean, the idea is very simple, right? We have a signal X, we have a kernel W, and then the way a convolution works is that the kernel slides over the input, and at each step of this process, we take a dot product between the kernel and the patch we're currently overlapping with. Now, the thing that makes convolutions much more tedious is that there's tons of parameters to kind of modify how the kernel slides over the input, but we also have a lot of additional features. For example, we want to do things in batch mode, or we want to group the channels into groups and then do convolution separately on these groups. So if you combine all of that and look at a fully fledged 1D convolution, you can see that this quickly becomes very complex. So here we have padding indicated by the blue pixels. We have a non-trivial stride, so the kernel slides over the input faster. We have a dilation between the elements of the kernel. We have multiple input channels, multiple output channels, we have batch dimensions, we have groups, so we can handle things independently over channel groups. And then this is 1D, we will do everything in 2D, maybe even 3D. This is what makes convolution a lot more complicated than just linear layers, but at their core, they are just dot products, right? So there should be a way to kind of view them in a unified framework. And this framework is tensor multiplication, or the nicer way to think about tensor multiplication will be tensor networks, which is basically a graphical way to think about the operations. So I want to, really make you understand this. I'm going to go from the basics. Let's just look at what the operations are that we can do with vectors. So we can do a dot product, we can do an element-wise product, we can do an outer product, which happens to be a chronicle product. And you all know how these operations are defined in terms of indices. And we can do the same thing for matrices. Again, we have like a matrix product, element-wise product, chronicle product. But we actually have many more operations, and you can see this if you look at the indices. So in principle, we get two objects. They each have two indices, and we need to build another object which can have 0, 1, 2, 3, 4 indices. So there's a lot of freedom here. But what is interesting is that we can infer what we have to do by just looking at the indices on the right-hand side and the indices on the left-hand side. Because if an index doesn't show up on the left-hand side, it means that it was summed out. It means that there was a sum, so we took a dot product on the way. And this is exactly what tensor multiplication uses to kind of generalize the notion of dot products, matrix products to arbitrary tensors. So if we were to give a mathematical definition of this operation, I'm just showing this to kind of make the point that this is not how you would want to work with these expressions because it involves a lot of indices. It would look somehow like this. So if we wanted to multiply two tensors, A and B, we would have to specify the ingoing indices as A, as B, and the outgoing index as C. And then we could infer which indices have disappeared, so they must have been summed out, right? It's much easier to just go through an example. So if we consider matrix-matrix multiplication, we have ingoing indices ij, jk for matrices A and B, and the outgoing indexes ik, which means if we do this magic set arithmetic, that the index that was summed over was j. So that's the rough idea here. This is how everything works in general. Now, what we will do in code is that we will take these indices and encode them in a string. So we will say we have two matrices, AB, indices ij, jk, and they map to a new tensor, ik, as follows. And then Einsum will infer what are the summations that need to be carried out and will automatically do everything under the hood. So this is what Einsum is. It also works not only on two tensors, it works on an arbitrary number of tensors, which makes the expression even more complicated. So the point I want to make here is that we really don't want to work with equations here. It's a nightmare. You need to parse the equations, you need to look where are the indices. So while it's nice to show some mathematical properties of this operation, it's not very convenient to work with it like that. And therefore, we want to translate it into a graphical approach, because graphical expressions are much nicer to parse. They're also more fun to work with because you can draw pictures and manipulate them. And they're actually mathematically equivalent, so we don't lose any expressive power by doing that. So a tensor network consists of these boxes, and a box is a tensor. And a tensor can have legs, and the number of legs determines the rank of the tensor. So a matrix has two legs because it has two indices. We can combine indices, kind of take two indices and combine them into a single one, or we can do the opposite by taking one index and kind of turning it into two indices, which is indicated with this triangle notation. And to indicate operations, summations, we can connect two indices with a closed line. So for example, if we wanted to take the trace of a matrix, we would identify the row and column index, and then we would sum over them by closing the loop. And now you can see that the resulting tensor actually has 0 legs because the trace is a scalar. Now we can write down these operations we saw earlier on matrices. So for example, if we wanted to multiply two matrices, we will just put the two boxes for the matrices and connect the column index of A with the row index of J. If we were to compute element-wise products, we would connect the row and the column indices, but not close the connection because we don't want to sum. We want to preserve the index, so we'll have a leg sticking out. And if we were to do a chronicle product, an outer product, I think is actually very literal here. you will just place the two tensors on top of each other and then kind of bring them back into matrix land by using these triangles and combining the four indices to two indices. Right? So this is basically tensor networks on a single slide. I know this is maybe a little bit confusing, but we'll see later a lot of nice pictures. And you can translate these expressions back to math anytime and also convert them back to Einsum anytime. I will skip this part here due to time reasons. But so I want to talk a little bit about what are the benefits of doing that, because I feel like it's really a cool tool to use tensor networks. I use it a lot. And if you take anything from this talk, I would say you should use Einsum in your code. The first reason you should use it is that you can explicitly document the shapes of your tensors, because you can just add that you can assign names to each axis. You can say this is a batch axis, this is an in-channel axis, etc. And then you don't have to have external comments, which might get outdated over time because nobody updates documentation. The second thing, or the second aspect would be you can not only write readable code, you can also write efficient code, because Einsum will automatically figure out what's the optimal order to contract things. So here, if we want to take a matrix-matrix vector product, there's two ways of doing that. There's the dumb way of multiplying A onto B, and then multiplying that onto V, which is a matrix-matrix product, and then a matrix vector product. And there's a smart way, which will multiply B onto V, and then A onto the result of that, which would be only two matrix vector products. And Einsum will automatically figure out what's the best order to do that under the hood. You don't have to do anything. So from a coding perspective, Einsum is very nice. Now, from an analytical perspective, it is also very nice because we can draw these diagrams and manipulate them to do things like function transformations. So for example, if we want to V-map our operation, introducing a batch axis, so to say, all we have to do is we just add an additional axis for each of the tensors, which is the batch axis, and then we connect them and let the legs stick out to indicate that we want to do everything on a per datum basis. And the second operation, which we'll use later on, and which is also very relevant to optimization because we want to compute derivatives there, is differentiation. I think this is actually a very cool illustration here of how you can take derivatives the lazy way, because differentiation is just removing tensors. So if we were to differentiate our expression with respect to B, we only have to remove B, that's it. And here you can already see some interesting structure because the Jacobian now consists of two disjoint diagrams. And this means that the Jacobian has a Kronecker structure. And we can do the same. We can take the derivative with respect to A. Then we just introduce an identity matrix on the left. And then we remove A. And then we get a Jacobian, which again has a Kronecker structure. So this way you can see how derivatives like Jacobians or Hessians get a Kronecker structure, because if you remove a tensor, it's likely that you get two disjoint diagrams. Okay, this concludes the tutorial on tensor networks and why they're cool. Let's apply this stuff to convolutions and see if we can actually get something cool out of it. So we have to very quickly look at how a convolution works and how we can turn it into a tensor network. And for that, we need to start from the index notation. So we have the kernel, and the kernel takes a dot product with the current patch it overlaps. So we kind of need to figure out what are the elements in the signal that the kernel currently overlaps. And so this position I in X is determined by which output element are we currently generating and what's the kernel element, K. And to make this less implicit, we will introduce a new tensor that kind of tracks the connection between which element in the input couples the kernel to an element in the output. And if you want to visualize that, you can just monitor the blue pixel here as the kernel slides over the input. You can see how the first element of the kernel couples input elements in X to output elements in Y. So this pi tensor is very sparse in practice. And the good thing now is that we can take this expression on the left and just convert it back into a diagram. And this gives us a tensor network for 1D convolution. And now, from now on, we can just apply everything we learned before and have some fun drawing and looking at diagrams. So this is a 1D convolution. What if we want to go to 2 dimensions? Well, the way the kernel slides over dimensions is independent along each dimension, right? So all we have to do if we go to 2 dimensions is we will introduce a new pattern tensor for the new dimension and add the contractions with the input dimensions and kernel dimensions. And for 3D, we do the same. We add a new index pattern tensor for the 3rd dimension, and so on. We can repeat this to arbitrary dimensions. We can also take derivatives, because derivatives is just removing tensors, right? So let's do that real quick. We can take the convolution and remove the weight. Then we will get this Jacobian. We can remove the input. We will get this Jacobian. This might be interesting if you're doing some kind of theoretical analysis of the Jacobian. But what I was interested in the context of this paper is the operation that autodiff performs. So this vector Jacobian product, which is taking the Jacobian, multiplying it with a vector. And you can see this here on the top right. And now, if you remember back on slide 2, we had this very long expression for weight vector Jacobian product with 50 lines of code. We can now do this with 3 lines of code. We need to generate pi 1, pi 2, and then we need to evaluate this diagram with a call to Einsum. So now we've simplified the 50 lines into 3 lines. And I cannot really talk about this too much, but if you do this for the input, this is actually a transpose convolution. So there's some nice follow-up things you can do based on this insight that the input VJP is a transpose convolution. But I don't have time to talk about that. There's actually a lot more pictures in the paper, which demonstrates not only Jacobians, but also Hessian matrices and all things people have come up with for convolutions. And I quickly want to I hope now I kind of made a case that drawing diagrams is cool and is a little bit more intuitive than writing down everything in index notation. I want to quickly show you that this is not just fun, but you can actually get real speedups in applications. So I want to show this in the context of KFAC, which, don't worry, you don't need to know. Just think about it as a non-traditional operation that people want to perform. So people like me who are working on second-order methods, we often have to do more exotic operations, and these are not always well supported by libraries like PyTorch or JAX. So the way one would compute KFAC in a state-of-the-art implementation would be you would take the input to the convolution, you would extract the patches and align them into a matrix, then you would average the patches, and then you would take the outer product of that. You can look at this as just a tensor network. And now the interesting thing is that because we are using some machine learning framework, the way we would have to do it in PyTorch is, and we would have to build up this huge tensor, the unfolded input, it is called this X double bracket, which is very slow, and here roughly 4 times slower. And also it has to build up this huge intermediate tensor, which means that it also uses a lot more memory. So if we use our tensor network implementation to do that, we are 4 times faster and we don't need any extra memory. So taking this thing, or you can kind of view this as a placeholder for any non-traditional operation related to convolution. We took this operation and we integrated it into an optimizer that got published at ICML this year. And also here it showed like real speedups on this method. So we compared this with gradient descent, no momentum. And if you just use the state-of-the-art implementation with PyTorch, you will see that the optimizer has like an overhead of maybe 50% to 70% in terms of time. And the memory overhead can be, well, on Resonant, it was only 25%, but on BTG, it was more than 100%. It was using more than twice the memory. with this tensor network trick, we were able to reduce the runtime overhead by 50%. And we were able to almost completely reduce the memory overhead. So if you look at the memory consumption for a VGG19, you can see that compared to the original PyTorch API solution, the tensor network implementation basically halved the memory, which is great because now we can run this on a single GPU and not on a big GPU. So the tensor networks are actually useful in practice too. And I think I want to quickly conclude and hope that I convinced you, A, tensor networks are really cool. You should, you should use Einsum in your code. Then now, thanks to this approach, we have a lot of methods like vector Jacobian products, Jacobians, Hessians, which we can work with just as Einsums, just using Python, because usually those methods are written in some low-level language like CUDA or so, which makes them really hard to modify. So if you have any ideas, try them out. Randomized automatic differentiation, etc. This approach will allow to do that very easily. And then you don't have to worry about anything. Einsum will automatically figure out what's the best way to do the tensor contraction for you. And if you want to try out some of the operations I talked about here, there's actually a lot more in the paper. There's also a library that I'm releasing with the paper, which basically allows you to generate the tensors I was showing you and then just evaluate the tensor network using Einsum. So yeah, if you have any cool ideas how to, I don't know, approximate weight matrices in LLMs, or if you work with tensor networks and you're interested in incorporating the inductive bias of a convolution into your tensor network, feel free to reach out to me. And yeah, questions welcome. Thank you. Maybe we can use the microphone.
So this paper is mainly to improve convolution network. So will it possible to be extended to the current neural network or something else?
So that depends a little bit. As you may have noticed here, tensor networks are all about tensor contractions, which are multilinear operations, which means that if you have a nonlinearity at some point, this will usually break the graph. So if you have a recurrent neural network and it has some form of nonlinearity, then you will probably not be able to use tensor networks. Yeah, Agustinos?
So you mentioned that you should just use Einsum for everything, right? But there is no free lunch, right? So what's the catch here? So what's the cost? Is the cost is it's well worth to pay the cost because it is much harder to screw up in our code, or is it actually not very economical? Its own cost of using Einsum everywhere.
Yeah, I think the promise of Einsum is that it will really handle all these headaches for you automatically. I think the current implementation probably has some edge cases where it fails to kind of dispatch onto the correct or the most efficient operation. Also, so I would generally encourage everyone to write Einsum because it makes the code very readable and ideally also optimal in terms of performance. Yeah, so I'm not sure. I think in general it's a very good way of writing code with Einsum.
But the way I see it, that's because it's for general, right? And then therefore you need to have some kind of inference engine in the Einsum itself.
Yeah.
That's need to this one is the one that we need to contract first, and so on and so forth. So that would be an overhead, right?
Yes, that would be an overhead for, let's say, very large tensor networks. For small tensor networks, I think you pay very little overhead to figure out what's the optimal order. You can also pre-compute that. And I believe if you were to compile an Einsum expression, it would actually only figure out the contraction path once and then just cache that.
Thanks.
Any more questions? Okay, if not, let's thanks Felix again for your great
Thanks.
talk.